So today our focus is going to be on doing those same critical points, those extreme values, but we're going to be focusing on using our graphing calculators to do that as opposed to doing the algebra like you were doing yesterday by hand. Okay, what you're doing is something called the first derivative test. This analysis that you're doing, finding the pluses and the minuses and the minuses and the pluses, that's called the first derivative test. Okay? All right, so let's review yesterday. We talked about what it means to be a critical point. And critical points come from two places. They come from equal to 0. What kind of tangents are those if it's equal to 0? Horizontal. Great. And then we also, don't forget about undefined, which is 1 over 0. What kind of things are that? Vertical tangents. What else? Could be cusps, could be corners. And right, all of this is under the assumption that the f of x is what kind of function to begin with? Continuous. Okay, we have to have continuous functions. All right, if we have endpoints, then we have a closed interval that we would check as well. So we would remember to check the endpoints. The extreme values are the y values that go with all the critical points. I have that a lot where I'll ask for an extreme value and I'll get just the x coordinate, but they'll fail to give me the y coordinate as well. If I want an extreme, I need to know what the y coordinate is so that I know it's the extreme. Okay, because I need to know it's not a local, it's an absolute, so give me the y coordinate as well. So that would be another area that people might, on a multiple choice, say. I might put the x coordinate on the multiple choice and I would put the y coordinate, and I want you to pick the y coordinate because that's what an extreme value is. And so what you did yesterday is you were looking for if it had endpoints and if it had the critical points and then testing the y values to find out the extreme values. So that's just a review, everything we did yesterday. Here's a similar chart or graph to what we looked at. Okay, if we were making this into a chart, if we were dividing it up into intervals, we would have pluses and minuses all over. So what we would have here is this would be a plus section. Why would that be a plus section on a chart? Okay, because it has a slope that's going up. And then I would have it followed by another plus section. Because it was going from plus to plus and there was no change, then there is no extreme value there because you were going from plus to plus. It doesn't have an extreme value unless there's a change. When I change to negative and going down, then I have some kind of extreme value, either a max or a min and a local or an absolute. And then we would change to plus again, and then we would change to minus, and then we'd have a double minus, a minus to minus, which doesn't mean anything either. It's no extreme value. The important thing is the change. And when you write your sentences, if you don't have the word change in there, it is changing from blank to blank. You can't get the full points for it because that's the important part, that the change happens. Some students will just say it has a max because, and then all they tell me is that the derivative is equal to 0. I say, that's not enough because there's an example of where there's a derivative equal to 0 right here. But it's not an extreme value at all because there was no change around it. The word change is going to be a very important value. All right, so just to re-emphasize what we're doing, if the change is from plus to minus in any kind of way, this is a plus changing to a minus, that creates a max. So if you are going to justify your answer, and you're telling me it's a max, you have to say because the derivative changes from positive to minus. That could be on a parabola type piece. It could be on a cusp type piece. If it changes from minus to plus, that is your min. That is the definition. And then finally, if it's plus and stays plus, positive slope and still positive slope, or minus and stays minus, that's no extreme value at all. That would be none. All right, so I guess I can't emphasize that enough. The definition of a maximum, the presence of a max is detected at a critical point if the derivative changes from positive to negative, and then a minimum is detected if a derivative changes from negative to positive. Yesterday, all of your homework was analytically. You set an algebraic derivative equal to 0. You also set an algebraic derivative equal to undefined. You made a chart. That is called analytical derivative, okay? Today, we are going to focus on doing the same thing with a graphical. We are going to set a graphical derivative equal to 0 and a graphical derivative equal to undefined and do the exact same thing. All right, so here we go. Suppose this is a derivative graph, not a regular graph, a derivative graph. You want to set the derivative equal to 0, and you want to set the derivative equal to undefined, or 1 over 0. When you set a derivative graph equal to 0, you're looking for the places that it is 0. In other words, the places that it's crossing the x-axis. So this is equal to 0 3 different times. And so I would get critical points that are x equals, let's say it's ballpark, -5.5, and we'll say it's -3, and we'll say it's +3. Setting a derivative equal to undefined would be any places of discontinuity. This one doesn't have any. There are no places of discontinuity, so I don't have any undefined places. So in a derivative, what you're looking for are not the maxes and mins, because I'm not looking at a real graph. I'm looking at a derivative graph. The derivative graph, what I'm looking for is setting it equal to 0 or places of discontinuity. All right, so for these, I have the intervals. So I'm going to set them up as follows. I'll have x less than -5.5. I'll have -5.5 up to -3. I'll have -3 up to +3. And then I'll have all x's greater than +3. As I'm analyzing this graph, I am not looking for whether the graph direction is going up or down. I'm looking at whether it's above or below the x-axis, because you're looking at a derivative graph now. We did this with velocity before. I'm not looking for the slope itself. I'm looking for whether it's above or below the x-axis. So as I analyze this section that is less than -5 is above the x-axis, so that would count as a plus. The next section is below the x-axis, so that would count as a minus. And then we've got a big plus section, and then another minus section. So reading a derivative graph is different than reading a regular graph. Now, once we have the chart, it's pretty easy to tell where there's going to be a max and where there's going to be a min, and where the increasing intervals and decreasing intervals are going to be. So it's the same as yesterday. This would be an increasing interval changing to a decreasing. That means the original graph, which we can't see right now, is following this behavior. The original graph is looking like it goes increasing to decreasing. And if it does go from increasing to decreasing, then we're going to have a max in between those two intervals. And then when it changes from decreasing back to increasing, we're going to have another min. And then again, as it changes from increasing back to decreasing, we will have another max. And there are no endpoints on this, because my original graph didn't have endpoints. So if I were to ask you to sketch something that does that, you should be able to make a graph that follows that behavior. Draw something that increases, hits a max, changes to decreases, hits a min, changes to increasing, hits a max, changes to decreasing, hits a min. You should be able to sketch something that does this and this and this, and then back to that again. Okay, it does not need to be perfect. It just needs to follow the behavior that you said it would. Okay, let's let's try another one. Here's another derivative graph. You set the derivative graph equal to 0 and set the derivative equal to undefined or discontinuous and see what you get. When I set this derivative graph equal to 0, I see that I get 1, 2, 3 again. And there are no points of discontinuity.
Even if it barely touches,
it
doesn't have to cross to be
doesn't have to cross. Okay, so then we set up our chart. X less than B, X from B to D, X from D to F, and X greater than F. This one, excuse me, does have endpoints because there are no arrows on the ends of my graph here. So I need to adjust my intervals and put endpoints on there. So it'll be F stopping, so equal to G, because it's stopping at G. And then my first interval, it would include the A. Okay, so I do have endpoints. Then you're going to analyze it with above and below. So below the endpoint or below the x-axis, that would be a minus. Above the x-axis, that would be a plus. Below the x-axis, a minus. And below the x-axis again, which would be another minus. So notice that is a key feature. It's a minus and then stays a minus. So what's happening at F? Nothing. There's no max or min at F, right? Nothing is happening at F. So we have decreasing. All right, if you start with a decreasing interval, so the graph starts going down, what does that mean about the end point of A? Okay, if you start somewhere and all you do is go down, okay, so it started with a max. And then when I change from decreasing to increasing, that will be a min. When I change from increasing back to decreasing again, that will be another max. But then because I stay decreasing, nothing important is happening at F. It's not an extreme value. It's not a max or a min. And then what about at G if you have decreased until you hit your endpoint? That'll be a min. So could you draw something like that that started at a max, went down for a while, changes to a min and goes up for a while, changes to a max, goes down for a while, and then goes down some more and finally ends at a min? Could you sketch that? That would be the idea. Okay. All right, so now we want to pull back to what we did with, you should have this in your calculator from yesterday. So can you pull up your calculator and go to your Y1, and you should have Math 8, so you should have ddx, and you should have this in your calculator. And if I remember correctly, it kind of looked like a cubic a little bit.
Yeah.
Okay. Yeah, can you zoom in on the origin? So go ahead and just sketch what you see. It's zoom number 6. Okay, and then zoom, and then you can hit enter again once it's done drawing. You just hit enter, it'll zoom on the center. Okay. Sorry, I think I told you the wrong thing. Oh, zoom 2, I apologize. Zoom 2, enter. Just with your X button, your variable button.
Oh, just X plus X?
Yep.
Okay.
Okay, so you have Math 8. Oh, you need to turn your plot 1 off. That's going to mess everything up. Okay, Math 8, so ddx. And then you're going to put the equation in there. All right, so everybody hopefully got it zoomed in.
Yeah.
Nice. Okay, So what you're seeing, what you should see, it's always a good idea to sketch what you see so I know that what you're looking at. So you've got this kind of a thing going on here. And so you want to set your derivative, which is what you're looking at, equal to 0, and set the derivative equal to undefined, which would be any discontinuities, which we don't see. So I only see one place where my derivative is equal to 0. That's right here. That appears to be at 0. So I only have two intervals to set up, x less than 0 and x greater than 0, and I don't have any endpoints. So the x less than 0 part is going to get a minus. The x greater than 0 part gets a plus, which means the original graph would be going from decreasing to increasing, meaning that I would have decreasing, changing to increasing, which would mean the definition of a min. Great. Okay, that's not so bad.
But it can't be an absolute value because there's no.
We don't have endpoints, right? Okay, and we don't have a function to check. Yeah, we don't have an extreme value because we'd need the y coordinate. We don't have a y. Okay, now change your equation to this one. So you can just use your y1 again, and you can change it to this. You don't have to really change anything else. And then let's take a look at what this derivative looks like. And we'll sketch what we see. It does take a little bit. Okay, so I want you to zoom, make your zoom a standard zoom. Oh, you've got something weird down there. Why don't you clear that? Okay. Now do a zoom 6, which is a standard zoom. There you go. Okay, so most of you, I'm seeing something that does this. It comes down and then kind of looks like this. Does it cross again, or does it just get really, really close? Does it ever cross? All right, so we're looking to set this equal to 0. And undefined. We don't have any undefined. There's no discontinuity here. All right, now you're going to have to calculate that spot. So do you remember how to do that on your calculator? Second calc, and to find the 0. So use your calculators now to find that 0. Go to second calc.
Wait, yeah, you put it right.
You're not getting that picture?
I fixed it.
I forgot to change it from the last.
All right, so now do second trace or second calc and calculate the 0. I need to a couple good decimal points.
Wait.
Does anybody have that yet? What is that value? X is less than what number?
Yeah.
1 point what?
It's 1.
Okay, 0, 0, 5. And then X is greater than.
Left to right.
Okay, so then we're going from a plus to a minus, which means we are going from increasing to decreasing, which means the original function has a max at that critical point. So we would be going from increasing to decreasing.